Hello students, today we will continue sharing about WLAN technology. In the last class we talked about heart binding, and in this class we will continue to explain the new binding of 2.44 gas WAN and the new binding of 5 GHz, as well as MIMO multiple input, multiple output technology. The new binding of 2.4 gas. In our last class, when we talked about the new binding, it was already mentioned. For example, we will distinguish the main heart channel and the auxiliary channel on the label, using a plus to indicate the main heart channel and a minus to indicate the auxiliary channel. In addition, in the case of 80 MHz binding, usually it is represented by the central bandwidth. This binding method can efficiently utilize channel resources. We also mentioned this in the last class, right? So in this 2.4 GHz frequency band, there is usually only a 40 MHz bandwidth, and therefore we won't display it specially. Let's take another look at the new binding in the 5 GHz band. Now, with an 80 MHz bandwidth, the channel performance will be different. In the 2.4 GHz band, we usually only use a 40 MHz bandwidth. So the binding and bandwidth representation is relatively simple. However, in the 5 GHz band, the bandwidth resources are more abundant. Especially with 80 MHz and 160 MHz bandwidths, the division and representation of channels become more complex. In the 5 GHz band, bandwidth resources are usually represented using the center channel, which means you need to specify the exact channel range. For example, with an 80 MHz bandwidth, it typically resembles this. Using 149 plus this way indicates that channel 149 is the primary channel and extends to higher channels such as channel 153. This representation helps to clearly display the channel bandwidth and ensures that network devices can correctly understand the bandwidth usage of the frequency band. Therefore, in the 5G band, the specific bandwidth must be clearly marked. Otherwise, it may not be displayed and used correctly. Without additional bandwidth information, the device cannot understand the actual configuration of bandwidth resources. Next, let's take a look at MIMO, multiple input, multiple output technology. This technology transmits data simultaneously through multiple antennas, thereby improving the transmission rate and reliability of wireless signals. In the traditional single antenna scenario, signals are transmitted through one transmitting and receiving antenna, which limits the data transmission rate. However, with this technology, multiple antennas can work in parallel, increasing the transmission paths of the signal. This enhances bandwidth and reliability. For example, when using a 2x2 MIMO configuration, there are 2 transmitting antennas and 2 receiving antennas, allowing the transmission of 2 spatial streams of signals, thereby achieving higher transmission rates. Although signal reliability can be improved through multiple paths, such as 4 paths, the actual number of transmitted spatial streams is still limited by the number of antennas. In this case, although there are 4 paths, the number of spatial streams transmitted is usually 2, because each antenna can only receive and send 1 data stream at a time. The core advantage of MIMO lies in increasing the number of spatial streams, that is, transmitting multiple signals simultaneously, and ITcertification, which can enhance signal reliability and network throughput. For example, with the same bandwidth, MIMO technology improves data transmission stability and speed by increasing the number of antennas. In summary, MIMO technology can improve the transmission capacity and stability of the network, while the increase in bandwidth depends on the number of antennas and the configuration of the spatial streams of the signal. Next, we have a technology called MIMO. What kind of technology is it? It is an extension of MIMO technology that allows multiple devices to simultaneously communicate with a wireless access point, AP, thereby improving the efficiency and throughput of the wireless network. In traditional MIMO, data transmission can only occur with one device at a time, whereas MIMO can support multiple terminal devices transmitting data simultaneously, thus enhancing bandwidth utilization. if we talk about the working mechanism of MU-MIMO, if there isn't one. That is, if there is no MU-MIMO, each terminal takes turns using the bandwidth for data transmission. For example, at T20 Mbps bandwidth, 3 terminals take turns receiving data, and each time only one terminal's data bandwidth will be divided among the other terminals. However, if you enable MU-MIMO, the wireless access point, AP, can allocate 100 megabits. Bandwidth is simultaneously allocated to multiple devices. In this situation, the AP can send data to multiple terminals in parallel. Each terminal can independently receive data without taking turns, thereby maximizing the utilization of bandwidth. The advantage of MU-MIMO technology is that it treats the antennas of multiple users as a whole. MU-MIMO can effectively enhance data transmission rates in our Wi-Fi 5 standard, which is 802.11 AC. In this standard, it refers to supporting downlink, which is communication from the AP to the terminal, meaning only the AP can send data to multiple devices simultaneously. However, in our 802.11ax, which is the Wi-Fi 6 standard, MU-MIMO technology has been enhanced to support not only downlink transmission but also uplink, meaning transmission from the terminal to the AP. This greatly improves the efficiency of multi-user concurrent transmission. With the implementation of MU-MIMO, when devices support MU-MIMO, even if there are multiple devices, they can also perform parallel data transmission through the AP as if operating multiple devices as one large device. This technology distinguishes data and sends it separately to different hardware facilities, enabling the ability to send signals to multiple terminals simultaneously. In Wi-Fi 6, both uplink and downlink MU-MIMO are supported. This makes the network more efficient, especially in high-density environments, significantly enhancing network performance when multiple devices are online simultaneously. Finally, regarding iMIMO, let's talk about beamforming, which is closely related to the phase enhancement and phase attenuation we mentioned earlier. Especially in MIMO technology, multipath transmission can cause signals to arrive at the receiver through different paths, resulting in different phases. When these signals mix, phase attenuation may occur, meaning the signal strength could decrease. If beamforming is not used, signals with multiple different phases may interfere with each other when superimposed, leading to a decline in signal quality, gain. The role of beamforming is to automatically adjust the phase of each antenna so that the signal is enhanced in the target direction rather than attenuated. In this way, beamforming can effectively improve the signal-to-noise ratio, thereby improving the quality of transmission. Simply put, beamforming optimizes the phase of the signal to ensure it is transmitted in the correct direction, avoiding the effects of interference and attenuation. This is also crucial for enhancing the performance of MIMO. Beamforming is closely related to the phase enhancement and phase attenuation we mentioned earlier, especially in MIMO technology, where multipath transmission causes signals to arrive at the receiver through different paths, resulting in different phases. In Wi-Fi 6, new optimization technologies have been introduced, among which OBSS, known as Overlapping Basic Service Set, is one of our most important concepts. It refers to a fixed AP, which is a wireless access point, and a network unit composed of multiple terminal devices. For example, an AP connected to 2 terminal devices constitutes a BSS. In this situation, the terminal devices connect to a specific AP. This AP and the devices within its coverage area together form a unit. If there is another AP in the adjacent area of a basic service set, the overlap of the signal coverage area with AP1 forms an OBSS, or overlapping basic service set. In this situation, the terminal will not only receive data from its own AP, but also simultaneously receive data sent by the adjacent AP too, which can cause issues. So, how do we solve this? For example, these competitive resources reduce transmission efficiency and co-channel interference intensifies. How should we avoid these issues? This requires us to learn the BSS carrying technology. In high-density scenarios, Wi-Fi network interference is very severe. For example, in a stadium, there may be thousands of devices connected to the network simultaneously, and the AP deployment space in each area is very limited. At this time, signal interference and transmission instability will affect the network's performance. Therefore, a new technology called BSS, carrying basic service and coloring, was introduced in Wi-Fi 6 to reduce interference and optimize network performance. How does BSS work? It is like this. BSS detection involves the AP and terminal detecting the use of the same color on the same channel. BIS. Second, conflict reporting. If the terminal detects a signal conflict with another AP, it will send a color conflict report to the AP. After the AP receives this conflict report, it will adjust its BSS color, that is the color, to avoid interference with other APs. For example, an AP originally using this pink color might change to a yellow marking. And then it can also go to avoid interference, because by adjusting the color, it reduces signal conflicts, which can improve the efficiency of our network. This is BSS coloring. Its feature is a technology that combines the physical layer and the MAC layer, using the BSS current field in the header of the physical layer to distinguish different network connections. By distinguishing the color of the physical layer field, Wi-Fi 6 can optimize the contention behavior of the MAC layer, helping terminals and APs share the spectrum more efficiently in crowded environments. This reduces interference. Therefore, BSS coloring is an important technology in Wi-Fi 6 for improving network performance in high-density scenarios by addressing interference. Next, let's take a look at the TWT, which stands for Target Wake Time. It is a power-saving mechanism introduced in Wi-Fi 6, suitable for IoT devices. TWT allows the AP to control the wake-up and sleep times of the terminal, thereby reducing unnecessary power consumption. The working principle is the scheduling of sleep and wake-up. There will be a schedule that indicates to the terminal when it can sleep and when it can wake up. This sleep time is usually very short, possibly just a few microseconds. But in this way, the long-term power consumption will be significantly reduced. So it also has a power-saving effect. TWT can reduce the unnecessary consumption of the terminal when idle, thereby achieving a 30% reduction in power consumption. This is very important for IoT devices that are online for long periods. And it avoids receiving something called a beacon. In traditional Wi-Fi, the AP will periodically send beacon frames. It sends once every 100 milliseconds, which increases the power consumption of the terminal. After using TWT, the terminal no longer needs to frequently receive beacon frames. Instead, it operates according to the schedule's instructions at the specified time. Thus, the terminal ultimately sleeps according to the TWT scheduling sleep time. Upon waking, data transmission is carried out through the AP's wake-up mechanism. Alright, that's all for today's sharing. If anyone is interested in Huawei's certification question bank, or in Huawei certification itself, or in my WLAN technology, feel free to leave a comment below my video.